Drill rigs like this are massive, multi-million-dollar operations, boring thousands of feet into the Earth's crust to reach trapped energy reserves. Deciding to put this rig in this exact spot requires a geologic roadmap, usually built using a surface seismic survey to map the underground rock layers. But those surface maps are essentially just acoustic echoes, and relying entirely on sound waves comes with a serious blind spot. Sound waves cannot definitively tell us if the microscopic pores in the rock hold oil, gas, or just water. So even if the structural map looks perfect, you can still spend millions drilling a completely dry hole. Energy companies are placing massive financial bets on an acoustic hypothesis. To validate that bet, they have to reach the rock and get physical proof. After weeks of drilling, the bit finally hits what engineers call target depth, and the borehole is flushed clean of debris. This is the moment of direct physical contact. The structural guesswork is over. To figure out exactly what is trapped inside that formation, we have to swap out surface acoustics for in situ direct physical measurements inside the well. Bridging the gap between a predicted model and a confirmed commercial discovery requires us to interrogate the rock itself. The heavy drill pipe is pulled out, and a specialized truck like this one takes over, lowering a suite of digital sensors deep into the earth on a high-tension steel cable. Once at the bottom, these sensors are pulled back to the surface at a steady, controlled speed, scanning every inch of the rock wall as they rise. The first tool in the suite is the gamma-ray sensor, which detects the faint, natural radioactivity emitted by the formation. This log creates a map of the rock type. Tight, non-producing shale contains naturally radioactive elements like potassium, causing the reading to spike high. When the line drops, it indicates clean reservoir rocks like sandstone or limestone. This radioactivity scan acts as an immediate filter, separating out the useless geological layers and pinpointing the exact boundaries of our potential oil-bearing zones. Knowing we have the right kind of rock, we then use density and neutron logs to measure porosity. This calculates the microscopic void space within the rock to tell us the total storage capacity of the reservoir. But having empty space doesn't guarantee oil. To identify the specific fluid hiding inside those pores, we rely on the resistivity log. This table breaks down the electrical signatures of the formation. Deep underground, naturally occurring saltwater is highly conductive, resulting in a low electrical resistance reading. Because crude oil and natural gas are insulators, they trigger a distinct high resistivity signature. This log chart shows the data in action, and floating in the center is Archie's equation. This formula takes those raw electrical resistance readings and converts them into an exact calculation of water saturation. By mathematically proving exactly what percentage of the pore space is filled with saltwater, engineers can subtract that figure and calculate the total volume of oil left in place. This chart compares the spatial resolution of exploration tools, highlighting the massive leap in precision. Where initial seismic surveys map structures in broad 50-meter blocks, wireline logs read the Earth in ultra-precise 15-centimeter increments. That granular data is necessary to calculate the net pay, which is the exact verifiable thickness of rock that actually holds commercial quantities of hydrocarbons. To guarantee absolute accuracy, engineers will extract these physical cylinders of the rock itself. These core samples provide a 1 millimeter physical reference point, used to calibrate the digital sensors back in the lab. By interrogating the well at this scale, exploration teams replace their theoretical geological models with concrete, verifiable economic data. The extreme pressures, heat, and complex physics thousands of feet underground have been securely captured and translated into clear digital metrics. This validated dataset now acts as the bedrock for the next phase of petroleum engineering, feeding directly into advanced predictive AI and full-scale digital twins of the reservoir. The reliance on surface echoes is left behind, securing the exact truth of what lies